All right, so here is a lecture about Eulerian circuits and trails in graphs. Um, and this is stuff out of chapter 5. So, an Eulerian circuit, which I'll abbreviate EC, is in a particular graph. It's a circuit. In other words, it's a closed trail. A trail is a walk, so it's a sequence of vertices such that your consecutive vertices on the trail are supposed to be adjacent. And a trail doesn't use the same edge more than once. And being closed means that you end at the same vertex that you started at. And it's an Eulerian circuit if it contains every edge. And keep in mind, I already said that it's a trail, so it can't use an edge more than once. And then I said it has to use every edge, meaning that it uses every edge exactly once. It can't use an edge more than once because then it wouldn't be a trail. So that's what an Eulerian circuit is. It uses every single edge, and it starts and ends in the same place. An Eulerian trail is like the same thing except it is open, meaning that it does not start and end at the same place. Like the last vertex is different from the first vertex. But it's still a trail, and it still uses every edge, and it uses every edge exactly once. So that's what we're going to be talking about today. And there's some nice theorems that completely tell you in a pretty easy way whether a graph has these things. So we started talking about theorem 5.1 last time, but let me fully prove it. So here's the theorem. Let G be non-trivial, so it has more than one vertex, and connected. Then G has an Eulerian circuit if and only if every vertex in G has even degree. So let's prove the forward direction, which we kind of talked about the proof of the forward direction, but I'm going to maybe state it in a slightly different way, or it's all equivalent, but it seems like a different way that I'm going to state it. So let's prove the forward direction. That means that, first of all, I'm assuming that G is non-trivial and connected. Second of all, I'm assuming that G has an Eulerian circuit, and then I'm going to show that that implies every vertex has even degree. So suppose G has an Eulerian circuit, and let's spell this out. A circuit is a sequence of vertices. So I have some sequence of vertices, and in particular, it's a circuit, so the first and last vertex have to be the same. And one awkward thing about this is a vertex might have several names, and we already know of a vertex in here that has two names. The first and last vertex have to be the same. And in general, a vertex could appear multiple times. Like there might be the same vertex that's like V naught, and then it's also V3, and then it's also V7. It might appear a bunch of times in this sequence. So that's what we have to think about. And basically, every time a vertex appears in the sequence, we say that we're visiting that vertex. Like I'm imagining sort of, if I have a picture of the graph, I can start with my finger on the first vertex and then move it to the next vertex and the next vertex and the next vertex. And as I do that, each time I point to a vertex, I say that I'm visiting it. And each time I visit a vertex, I use two edges. There's the edge that I use to come in and the edge that I use to come out. So this is what I'm saying here, and let me be careful about this. For any V that isn't the start and the end, It's a vertex that appears somewhere in the middle, and it's not the first vertex and it's not the last vertex. The degree is just 2 times the number of visits to that vertex, meaning it's 2 times the number of appearances that vertex makes in the sequence. And why is it 2 times? Once again, it's because every time the vertex appears in the sequence, there's an edge that I have that comes before it and the edge that comes after it, meaning the edge that I use to come in and the edge that I use to come out. Now, why is this different for the first and the last vertex? For the first vertex, which is of course the same as the last vertex, we start there and then we leave. So it's like we never really entered, right? We like just started there. We can imagine we just start there. We don't have to like use an edge to enter if we're starting there. So we start there and then we use an edge to leave. And then we might come back and visit that vertex several more times. And if we do that, if we visit and then leave and then visit and then leave, each one of those uses 2 edges. And then in the very end, we have to come back. In the very end, we have to come back. So once again, let me go through this. We start at that vertex and then we leave, and then that uses 1 edge. And then we might visit several more times, but every time I visit, like I'm going to use an edge to come in and an edge to come out. So there's the 1 edge that I used when I initially left that vertex. And then there's several more possible times that I visit that vertex, and each one of those accounts for 2 edges. So I'm going to have, like, if I'm counting the edges touching that vertex, I've got the 1 that I used to leave, and then 2 more for the first time I come back for a visit, and then 2 more for the second time I come back for a visit. And so I'm going to have a bunch of 2s. And so I've got like 1 plus 2 plus 2 plus 2, and this is all going to be an odd number. And then I come back, and that last edge makes it an even number of edges again. What I wrote on the paper is that the degree of that vertex is 2 times the number of appearances minus 1. Because actually this vertex appears an extra time, just expressing that, like, the last time that we come back, because we have to come back to where we started. So the name of this vertex appears on this list 1 extra time. So its degree is 2 times the number of appearances minus 1. Either way, the degree is even. Right, the degree of V is 2 times the number of appearances, or in the case that we're talking about, the first vertex, which is the same as the last vertex, it's 2 times the number of appearances minus 1. But either way, it's going to be an even number. Okay. Let's prove the other direction. So once again, here's the statement of the theorem. And so throughout, we're assuming that G is non-trivial and connected. But now I'm proving the backwards direction of this implication, meaning that I'm also going to assume that every vertex has even degree, and then my job is to show that G has an Eulerian circuit. So that's what I'm assuming. G is non-trivial and connected, and that all the vertices have even degree. And my job is to show that there's an Eulerian circuit. So I am going to let T be a longest trail. And as I usually emphasize, I did not say the longest trail because there might be a tie for longest trails. But I'm just saying that there isn't a longer trail. So I'm going to let that be T. And why am I doing this? If you think about it, an Eulerian circuit is, one way of thinking about it is just a very long trail. I mean, a trail is forbidden from using the same edge more than once. And so the longest it could possibly be is if it used every edge exactly once. And that's what we're looking for. So maybe it would help to just look for a trail that's just really long and just hope that that happens to be an Eulerian circuit. And that's what we're going to do. Let T be the longest trail, and then I'm going to claim that T is an Eulerian circuit, and I'm claiming something that I haven't proven yet, but we're going to prove it. So, but it helps to let you know that that's where we're going. First of all, notice that T must be closed. And I'll explain that. And so I'm claiming that T must be closed, meaning that the first and last vertex are the same. And I'm about to prove that by contradiction. So I'm going to suppose that it isn't true. So suppose that V0 and VL are different. Then T uses an odd number of edges incident with VL. Why is that? That kind of goes back to similar reasoning that you saw me use in the last, in like the other direction. So imagine that we have this trail, and this time imagine that V0 and VL are different vertices. Then how many edges do I use that touch VL? Well, VL might appear several times in the middle, and each one of those times accounts for two edges. Anytime a vertex appears in the middle, that accounts for two edges, because there's the one where you enter and then the one where you leave. But then VL also appears at the very end, meaning that there's like an enter that doesn't have a leave. Like I'm going to enter VL, but then I'm not going to leave because that's the end of the trail. So that last edge would make it an odd number of edges, right? So this trail, if it's not closed, would use an odd number of edges incident with VL. But we know that VL has even degree because all vertices have even degree, meaning that this trail hasn't used all of the edges that touch VL. Like there's an even number of edges that touch VL, and we've only used an odd number of them. So there must be an unused edge. Yeah, so that's what I'm saying here. There would be an unused edge to use that I could use to make T longer. More specifically, maybe I'll draw a picture. We have this trail. And, it can be kind of crazy. So it starts at V0, and then maybe goes here, here. Maybe it visits this one again. Maybe it goes here, and then ends at VL. And we know that there's an edge that's not part of that trail that touches VL. But I can use that edge to make the trail longer, right? There's obviously a longer trail where I just trace out the same trail that I had and then tack on that unused edge. That would be a contradiction because T is supposed to be a longest trail, that there's not supposed to be a trail that's longer than T. So that would be a contradiction. And recall, this is a small proof by contradiction because we are just claiming that T must be a closed trail. We're claiming that V naught must be the same as VL. And so we assumed, for the sake of contradiction, that V naught and VL were different, and then we reached a contradiction. So what we just concluded is that T really is closed, that V naught equals VL. We're still not done. We want to argue that T is an Eulerian circuit. So far, we have shown that T is a circuit, meaning that it starts and ends in the same place. But to show that it's an Eulerian circuit, we need it to use every edge. So we're going to prove that T uses every edge, and we're going to do by contradiction. So suppose for contradiction that T does not use every edge. In other words, T is not an Eulerian circuit, and yeah, so there's some edge that's not part of T. So maybe I'll draw another picture. At this point, we know that V naught and VL are the same. Yeah, maybe actually. Yeah, sorry, let me draw a different picture. I don't like that one. I mean, I want to draw a picture that's sort of complicated enough, but not too complicated. You know, because it can really be complicated. We can have a situation where we're visiting the same vertex more than once. So maybe here's a graph, and I have drawn, just to be clear here, this has the closed trail, say, yeah, actually, let me give this even another name, say X. So this has the closed trail X, A, B, so then I'll go to D, and then back to A, then to C, then back to D, and finally back to X. So yeah, I mean, I'm just drawing a picture here. But suppose that that this is not an Eulerian circuit. So there's some edge that's not in T. Whoops. Yeah, sorry. Let me not bungle this too much. In my picture, let me change the name of X to Z, because I just realized that in my proof I use another vertex whose name is X. So I just changed the X's to Z's. So that's not a big deal. If there's an edge of the graph that's not used on the trail, so imagine that this is just part of a graph, and that there's some other edge that obviously I haven't drawn, because so far I've only just drawn the trail. But there's some edge that's part of this graph that isn't on the trail. And there's a couple of ways it could look. There could be an edge that doesn't even touch the trail, like it's two vertices that aren't even ever visited by the trail. Or it could be an edge where one endpoint has been visited by the trail. Or it could be an edge where both endpoints have been visited by the trail. But since the graph is connected, if there was an edge like this that neither endpoint is even visited by the trail, then the graph has to have a path that connects these two to the vertices that are visited by the trail. In other words, even if I have an edge like this, there's a path that I can follow that will end somewhere on the trail. And so what I'm claiming here is that there has to be an edge of G that's not used by T, and that at least one of the endpoints is visited by T. If it's an edge like this, then it's obvious because one of these endpoints was visited by T. If it's an edge like this, then actually both endpoints were visited by T, and that's fine. We're just saying that at least one of the endpoints of the edge is visited by T. And if there's an edge like this, then this is no good. Like, this can't be my edge xy because neither one is visited by T. But what I do is I take the path there and say, like, here, the last edge of this path where it's about to touch T, I see an edge and one endpoint is visited by T. So that's what I'm saying. That once again, if T is not an Eulerian circuit, then that means there's an edge that does not get used by T, and in particular, there's an edge where at least one endpoint is visited by T. Okay. So since X is visited by T, that means that X appears on the list, right? Like T is this list of vertices. So if every vertex that gets visited appears somewhere in here. So say that it's V sub I. And then what I'm going to do is I'm going to get a contradiction by finding a longer trail again. So what do we have? At this point, so maybe on this picture I can say, like, point to this edge. This is an edge that is not used by the trail. And what I'm saying is that I can use that edge to make the trail longer. And how am I going to do that? I'm just going to, so here's the trick. What we have is a closed trail. T is a closed trail. We've already concluded that. And the thing about a closed trail is the starting point and the end point are kind of arbitrary. Because it starts and ends at the same spot, you can kind of choose anything as your starting point and then just go around, and then when you get to the end, skip back to the beginning because that's the same vertex, and then come back and end it where you started. So if this is my trail, once again, it goes from Z, A, B, D, A, C, D, back to Z. What I can do is, if I want to use this edge, then here's what I'm going to do. Instead of considering this as my start point and end point, I'm going to consider this as my start point and end point. Meaning I go C, D, Z. How does this go? Yeah, what I should do is just look at this. I go C, D, Z, and then I'm back to here. So I go to A, and then B, and then D, and then A again, and then C, and then this edge. So that's what I'm going to do. So keep in mind that X is V sub I, and what I'm going to do is I'm going to use the trail T, except I'm going to regard that as the start point. I'm going to start at V sub I, and then I go through the trail. So I go to v sub I plus 1, v sub I plus 2, and until I'm at the end of the trail, v sub L, and v sub L is the same as v sub naught, and then I go through, and then I'm back at the beginning of the trail, and then I go through until I reach v sub I again. And then from v sub I, because keep in mind, v sub I is the same as x, and x is adjacent to y, and this is an edge that I haven't used in the trail before, so I can then go to y. And this is a longer trail than t, because all I did is I took t, and it's the same length when I consider vi as the starting point. So I just went all the way around the same trail, and plus one more edge. So that's longer than t, and that's a contradiction. So actually, t must be an Eulerian circuit. Okay, so then, actually, okay, I'm going to stop this video and make a new one.